Hello everyone, my name is Hyung-Jeong from Chonnam National University, South Korea. And today I would like to present our solution for EV 2021 challenge with the title Temporal Convolution Network with Positional Encoding for Evoked Expression Estimation. So as you know, the Evoked Expression from Video Challenge 2021 have the video annotated as 6 head with 15 continuous expression in range from 0 to 1. So it means for each second we have 6 times time, and for each times time we will have 15 continuous expression. And in the training we have around 3,000 video, and for validation we have around 700. And for the testing we have 1,300. And for the testing we do not have the label, and we need to submit to the organizer to evaluate the score. And the video is come from YouTube with different kind of clips, from music to the video to the entertainment to the news, and we need to read the score for each time here. And the video have different lengths, from maybe from 80 seconds to 120 seconds or more. So our solution have two parts. The first is the feature injector, and the second is the estimation module, which include the temporal and the regression. So for the feature injector, we consider the two kind of information: the visual and the audio information. For the visual information, we read from its set head and resize it to the size of 224 by 224 to deal with the retrain model. And the retrain model will produce a vector with 1,280 dimensions for each frame. And for the audio, we resemble the audio to the 16 kilohertz, and after that we split it to the segment, and each segment will have the length of 1 divided by 6 seconds. From each segment, we will compute the log mass spectrogram with the size of 96 by 64, and after that we use regression models to extract the feature vector with the 2048 dimension here. And in the estimation module, we have the temporal and the regression module. For the temporal module, we build it based on the TCN residual block, the temporal conversion residual block. It consists of the related causal convolution and normalizer, such as the white norm, the rub out, and one by one convolution is used to ensure the length of the input to make the addition connection with the output here, similar to this residual connection. So we will stack up the multi-TCN residual block to make our temporal module. And for the positional encoding, we encode the positional of the time in the input sequence. So as you know, the training and validation set, the video have some missing. Some video, almost the video will have the missing in the annotation for sometimes time in the video. It make the discontinuous in the label. So we use the positional encoding to let the temporal module know the difference in time of the uh, of each time of each uh, time point in the input sequence. So in the recent module, we use two fully connected layer with the row in the middle, and we will show the parameter of the module in the next slide. So for the feature injector, we use the regression model on the TensorFlow hub, and you can find the regression model in link in the footnote here. And for the temporal and regression module, we use the ByTalk 1.8, and we train our network with 20 epoch on the training video, and we validate with on the validation set. We train with the HGD optimizer with the learning rate of 0.005 with the batch size of 32, and we use the objective function in the mean square error. So you can see here the NB here is the batch size. It means 32, and G here is in our training progress, we use we fit the whole video at a time to the network. So the batch size 32 it also means 32 video during the training, and so the Z here indicate the index, the video index of the batch size, and the NC here is a number of class. So in the EV 2021 we have the 15, so NC will equal to 15. And the Y here is the ground vector, and the Y hat here is the radiation vector, and the NGL here is the number of frame in the video Z. So here is our parameter for the temporal module and regression module. So we also try the for the virtual feature. We use 3 blocks of the descent residual. For each block, each will have the 512 filter the channel with the relation from 1 through and 4. And for the audio, we use 6 block of descent. So each block also have the 512 filter. And the relation is change from 1 to 4 and 1 to 4 again. For the hidden unit, we use 15 hidden unit for each fully integrated layer is corresponding to the number of class in the task. So for the kernel size, we use the same kernel size for both visual and audio is equal to 3. And in the evaluation metric, the EV 2021 use the Gaussian correlation coefficient to evaluate the submission. So the Gaussian correlation coefficient is range from -1 to 1, with the 1 indicate the perfect correlation, and for the -1 indicate the imperfect correlation. So you can see here in the table our result on the visual and audio. For the visual, we use the efficient net B0 with the rough out is 0.3 in the temporal module and the positional encoding which include. So we get the public and private score is similar, it's around 0.03. And for the audio, we have the 4 variant here. So let's see in the first two round here. They have similar with the dropout 0.3, but in here we have the first include the positional encoding, and the second it does include the positional encoding, and you can see the huge drop in the performance here. With the positional encoding, we have the score with around 0.05 on both the public and private test, but on the model with did not include the positional encoding, it dropped to the negative value in the -0.07 here. It's indicate the importance of the positional encoding in the network. So, and we are in the last in the near the due date, the deadline, we submit to different version of the audio with the dropout 0.2 and 0.0 here. So we did not expect that the improve on the result, but it showed that with the dropout 0.2, we get the best result on the published and the private test for the single model here. And the audio model with the dropout 0.2 also get the best score over on submission. And we also make an example of the audio and virtual model. So the example here is the weighted average of the virtual model here, the efficiency B0 here, and the first audio model here. The mobileness was improved with the dropout 0.3 with the positional encoding. In here, we indicate the audio. We have the last way is around 0.8, and for the virtual it is 0.2, and we take the average of the reason. So it make a huge improvement in here on the both published and private test. So as a summary, we present our approach for EEV 2021 challenge with beyond the design and positional encoding, and our approach achieved the first place on a private leaderboard. Our support will be publicly available at the GitHub link here, we are code here at the later day. And for the future work, we will consider the temporal information for the virtual data in each timestamp to try improve the result. And we also will try to learn directly the interaction between the audio and virtual during training instead of the live fusion, as you can see in the previous slide. That's all. Thank you. And we are waiting for the question from you. Thank you.